So I want to start off just by writing the kinematic equations. V is equal to VO plus AT. And then we have V squared is equal to VO squared plus what? 2a change in S. And then we also have, one second, made a mistake. And change in S is equal to VOT plus 1/2 AT squared. So these are our classic kinematic equations. Okay. And they're usually, pretty nice to use, right? What can we use them for? Well, we can use them for a ball going out of an airplane. We can use them for a ball going down a plane. We can use them for a lot of situations, but notice that I chose a ball where it's not really a ball, but it's more a particle. Okay, so we're just focusing on particles, so simple, systems, nothing too complicated, right? We're not worried about, the ball being hollow or anything like that. Then we kind of have to modify everything, but just a regular particle. Okay, now there's a way you can get these kinematic equations, derive them. I made a video on it, but there's another way you can do it using this formula. So we have d, the partial, d what? dt. And then we have dl. I'll make it a fancy L. And then ds dot. And that is equal to what? d dl ds. Okay, so this equation right here, we're going to box it because it's important. But it comes with another equation that is also pretty important with it. So that equation is, L is equal to T minus U. I probably should have wrote this one first. And I will make sure I drag this one up here next to it. So these are our two equations. Now what is this one called? This is the Euler Lagrange equation. So Euler, I'll say Lagrange equation. What is this right here? This is just Lagrangian. I have no idea how to actually truly spell that. Lagrangian. And what are this stuff? Well, this is kinetic and potential energy. Ke and Pe. So what it's saying is Lagrangian is equal to the kinetic energy minus the potential energy of the system. So the system being whatever it is. For us, our system is just a particle. It's just one thing. It's not multiple particles, just one particle. And the reason why we're doing just one particle is because it's easy, right? And then this is saying the partial derivative with respect to time for the Lagrangian. Then you take the Lagrangian's partial with respect to what? With respect to the change in position. So S, right? Earlier we said that S is our change in position. Well, delta S is our change in position, but S specifically is our position, okay? So now let's just think of the classic example, like I said, the ball going down. And then what can we do? Well, we can analyze and say that this thing has kinetic energy, which is equal to 1/2 mv squared. It also has potential energy, and we'll call this T, which is what? mgh. That's equal to U. Now, this is the fun part about using Lagrangian. Is unlike regular, mechanics where you're using Newton's, Newtonian mechanics, you need to have an established y and x, coordinate system, Cartesian coordinate system. Sometimes you'll even go to polar, right? Where you're going to be using, r and theta, right? And you'll see, you'll do that a lot, right? However, for Lagrangian mechanics, you really only need one coordinate. Okay? And the reason why you only need one coordinate, well, look at the equation. There's only one coordinate specific, right? And if you have that one coordinate, if you have like a common coordinate, right? So if you had a pendulum, that was a bad pendulum. I'll make it this way. If you had a pendulum, okay, so you have theta. Your common coordinate would be theta. If you have a ball dropping out the sky, you could use h, but we're going to use s because why not, right? The reason why we're going to use s instead of h is just because I wrote s over here, so it makes sense. Okay, well, nonetheless, so we know that v then is equal to s dot, right? Then we know that h is equal to s. Okay, so now if I write my Lagrangian, right? Lagrangian is going to be equal to 1/2 m s dot squared minus what? M g s. Okay. So again, all I did is just follow this equation right here. This is the first equation you're going to use. I'll write 1. I'll write 2 next to it. Okay. So if you use that stuff, we're going to get the 3 kinematic equations using this stuff, which may seem weird. Okay. So what we want again is d Lagrangian ds dot. So if we take this derivative and we look for the s dots, well, this term would be a 0, but then we do have something here. So we'll factor out the m and 2 because those are constants. We're going to do d ds dot applied to s dot squared. Okay, and remember mgs, it's just s. It's not s dot. So mgs itself is a constant when we are taking the derivative with respect to s dot. dl d Lagrangian ds dot is simply going to be equal to m s dot. Okay, right? Because we would see that the 2, right, this would become 2 s dot, and then the 2's would cancel, and then it would just be m s dot. Right, that's how it would work. Where's my... Let's go rewrite it. Okay, there we go. But then what else do we need? We need to also take the partial with respect to time. So now when we take the partial derivative of m s dot, we can factor out the m, and then we could write d dt, and s dot, this changes with time, okay, as change in time. So it's going to become this, and then what do we see? This is going to become m s double dot. And for a second, you see that this is the same thing as m times what? S, well, s is the change in position, so its derivative is velocity, and then velocity's derivative is acceleration, so this is ma, which is equal to force. So good, like we see something familiar, but for now, we're just going to leave it right here. This is what we want mainly. So I found one side of the equation. I found d what? dt, d Lagrangian, ds dot, and that all is equal to m s double dot. There's one more side of the equation. I have to do the right-hand side of the equation, which is what? D Lagrangian ds. Okay, so now I need to take, again, d ds for 1/2 m s double dot squared plus, well, not plus, minus mgs. And then as you guys can see here, that this guy will just become a 0, right? So then this just becomes negative mg s dot. No, not my bad. Sorry, we're just taking it with respect to s here. So this is going to be negative mgs. Negative mg. That's it. Sorry, I keep over speaking. Negative mg. So if we go back to our equation, d dt, d Lagrangian, ds dot is equal to dl, d Lagrangian, I mean ds. And we see that it's the equivalence of m s double dot is equal to negative mg. And then if we think about gravity, right? Well, what does this mean? We could write this as m s dot plus mg is equal to 0. And then we could factor out the m's. So then we just have s double dot. I'll make it look like a better does. S double dot is equal to gravity. And then you could say, okay, well, what does that mean? I mean, like, thank you. I know that acceleration is equal to gravity. Well, yes, good. You see that acceleration. So then if you take, so you can say a is equal to s double dot, which is equal to gravity. But then what happens if you integrate? So this is the sign for integration, the antiderivative, right? I'm sure you probably don't see it that way usually. But if we do d of s double dot dt, then we do the integral of what? The integral of gravity dt. Well, then this is gravity t plus some constant c. So basically, I'll go back here for a second. We'll write it like this. A, so s double dot is equal to g. So in other words, right, this is what? ds, right? One second. I don't want to confuse you guys. We'll just go back to here, okay? So we see that gt plus c is equal to s dot. So I really didn't want to confuse you guys right there. I was about to say something confusing. But then what is c? What is c? Okay, well, notice that gt, this is meters a second squared, and this is seconds. So then c, positive c, right, plus c, our constant, is probably some velocity VO, right? Because it's our initial condition, right? Comes from the initial condition. So then now this would make more sense to say we have s dot is equal to VO plus what? Gravity times t. And again, doesn't this look exactly like what we had? Where is it? Up here. So there we go. We just found this one. So we can check it off. Okay. And basically, right, if we do this again, so if we take the other antiderivative again, then we get that s is equal to the integral VO plus GT dt, which is equal to VOT plus GT squared divided by 2 plus C, right? We have our arbitrary constant. And as you guys can guess, right, if we take S, this is a position, so then our constant here is a position now. I'll just write SO for short. So in other words, S is equal to SO plus VOT plus GT squared over 2. And then earlier I had delta S, so S minus SO is equal to VOT plus GT squared over 2. So we'll box this one. And we should also box this one right here. And now we can cross this guy out. Okay. Now this last equation over here, delta S, oh wait, sorry, my bad. This is the one we had. This last one over here, v squared equals VO squared plus 2a delta S. Now that is an equation that comes from when we write acceleration, right? Acceleration as a is a function of what? Well, we write it as a function of position. So I'll write S. But for our sake, we wanted to know a as a function of t, right? So this equation and this equation over here, they're both timed equations. And that's what we really wanted. We wanted the equation of motion, right? We wanted the equation of motion for a time varying situation. So there we go. That's what we got.